Hello and thank you for joining. My name is Yves Lacroix. I'm the founder and president of YSystems Limited. In this short presentation, I want to talk mostly about the evolution of our wafer mapping product line over the past 20 years and how it has grown into a fully robotic multi-measurement instrument. I will show you some measurement examples from our laboratory and from some of our customers. As well, I want to discuss the instrument capabilities in the context of various applications. But first, let me introduce YSystems and tell you a little bit about myself. We are located in a relatively small city called Tokushima in the southwest of Japan, historically and even recently famous for its blue production. Actually, from over 200 years ago, Tokushima was the center of indigo production and its trade in Japan. More recently, as I'm sure some of you know, Tokushima has been at the center of blue LED industry. YSystems was founded in 2001 based on technology that I had developed over the years as a physicist. I always believed that in order to discover and understand new things, you needed to understand and, in most cases, build the instrument that could provide the information you were looking for. Although my primary interest was in situ measurement, since I hated, of course, waiting for the end of long growth processes, knowing exactly where to look on a wafer prompted me to develop a mapping instrument first. That eventually became the starting product of YSystems and is still now our flagship product. We did develop in-situ technology for various crystal growth systems, and much of our services involve the design of custom measurement systems and robotics. Our services include both mechanical and software design, fabrication, and machine assembly. However, in this short presentation, I will be focusing only on our mapping products. YWafert Mapper is actually a line of products which have a common software interface but are built in a wide range of hardware configurations. In the core design, there are two standard products currently in production, the GS4 and the RD8. The main difference being size, either for measurement area or the ability to accommodate various measurements within a single instrument. The GS4, which fits on a desktop and has a maximum 100 by 100 millimeter measurement area, can accommodate up to 4-inch wafers, but is still capable of mounting up to several photoluminescence wavelength excitations. The exact number, of course, depends on the size and the type of lasers. The RD8 system, which can be equipped with robotic wafer loading and measure wafers up to 8 inches, has a measurement area of 200 by 200 millimeters. As you will hear later, this has advantages even for small diameter wafers. It's not possible to give a comprehensive list of all available configurations. However, I will try to give you a general idea. As just mentioned, all models can be retrofitted with multiple excitation laser sources. Standard wavelengths are shown here, but of course this is not exhaustive. For the RD8, the switching of laser sources is fully automated. In the case of GS4, an external manual operated lever is used to change the optical paths. Now for the next 4 items, they are actually made possible due to our unique design of the scanning stage. All YWafert Mapper models allow for transmission measurement. In other words, both the front and the back side of the wafer can be excited or measured. This allows double-sided surface profiling, for substrate thickness measurement and backside optical excitation. Furthermore, in the case of YWafert RD8, because of the extended measurement area, multiple wafers may be loaded on a single tray. For example, using such a tray, 9 2-inch wafers can be loaded at the same time for measurement. We have developed a technology where multiple gratings and sensors can measure light simultaneously, allowing a range from 200 nanometers to over 2 microns of spectral data to be measured in a single acquisition. And just like for the laser excitations, there is no need to manually change detectors, gratings, or else. All components are built into the instrument. Optionally, we provide a fast mapping method for extremely low emission levels, although with limited spectral resolution. This option makes use of some of our very high sensitivity light detections developed for our institute products. Finally, of course, robotic wafer loading is available when batch measurement or even remote controlled measurement is required. As seen in the lineup description, robotic loading has 2 ranges of wafer sizes, either 2 to 6 inches or 4 to 8 inch wafer sizes. Nevertheless, manual wafer loading is always available for all wafer sizes, even for systems equipped with robotic wafer loading. Let me move now to some application examples. Standard photoluminescence is available from deep UV to far infrared. Developed for YWafert around 10 years ago, is a configuration which offers excimer laser light as a photoluminescence excitation at 193 nanometers. This deep ultraviolet excitation is particularly useful for the type of LEDs that are currently helping the disinfection effort in hospitals and other public places. Here is a map of wavelength distribution showing peak emissions around 270 nanometers. And for those familiar with aluminum gallium nitride, not only emission but transmission is a key factor for device efficiency. Therefore, substrate UV transmission measurement is also available as a configuration option. Defect concentration is another standard application of photoluminescence. One of our customers has been using a specially equipped RD8 for the study of deep traps in gallium nitride and has shown that PL mapping is a useful tool for run-to-run as well as in-wafer distribution assessment of carbon impurity concentration. Although the conclusion is that quantitative estimates are not trivial, PL mapping is effective in obtaining the distribution of carbon-related emission bands. The results were published last year at this conference in Colorado. Epitaxial layer thickness. The application of reflection and/or transmission mapping gives surprisingly accurate epitaxial layer thicknesses, even in the case of Homoepitaxial, where theoretically the material should not have any optical interface, as shown here. Moving on to more device-related applications, combining photoluminescence and reflectivity for VCSEL structure analysis is now, of course, a standard process. The YWafert spectral analysis allows mapping of just about any feature of a DBR layer, including mapping of the dip wavelength from the underlying cavity structure. Plotting the wafer cross-section of the dip wavelength, or even generating a map of the difference in wavelength between the DBR center and the dip wavelength is trivial using our standard mapping software. It allows you to generate a map out of the information provided from other maps or other physical parameters, such as the current wafer temperature. Alloy concentration is another parameter that can easily be extracted using this feature. Here we show a map of strain calculated from the indium gallium arsenide photoluminescence peak wavelength. The next application is less conventional due to the material investigated. YWafer mappers have been widely used for several years now to investigate phosphors, which can now be fabricated in the form of thin films or wafers for the use in modern LED fabrication. A standard white LED, for example, is composed of a blue LED partly exciting a yellow phosphor and partly transmitting. The resulting white light, however, depends on the balance of these two processes. In reality, the white light is not perfectly uniform due to a variety of physical conditions. YWafer can be configured to measure a map of phosphor plates by mimicking the white LED configuration and measure the emitted and transmitted light spectrum from multiple angles. Also, another important physical parameter, the thickness of the phosphor plate, can be mapped in detail and superimposed with the phosphor spectral characteristic maps for analysis. The resulting spectral parameters are mapped according to the position on the phosphor plate. In the case of visible light applications, the information may also be plotted on color graphs to predict the color dispersion within a phosphor plate. The last application I will talk about is curvature, or wafer stress measurement. Without affecting the photoluminescence configuration, YWafer can be fitted with high-precision optical sensors to measure the wafer surface position on the top or bottom side. Plotting this position in a map overlaid with other measurements allows calculation of curvature and stress, as shown here. The surface height across the wafer is fitted to a spherical curve in order to extract the curvature and its radius. In summary, YWafer Mapper is a versatile instrument which goes well beyond traditional single measurement mappers. By integrating multiple light sources and sensors, combined with practical and intuitive software tools, YWafer Mapper can be customized to serve your specific and increasing needs. Thank you very much for your attention, and let me also thank our customers and partners for their insights, suggestions, and amazing feedback, which allows us to continuously improve.